Hello everybody, my name is Dragan Djukic, Senior Engineer at EGSTON Power Electronics. I'm here to illustrate you the technology stack of EGSTON Power Electronics and show you all the interesting things that the company offers in terms of the technology developed and to show all the innovative layers that the company offers. More or less, one of the first things to understand about the company and the solution that it provides is that EGSTON Power offers turnkey solutions in power hardware in the loop market, and not only that, but also various solutions for test systems for big power electronics devices which range all the way to up to 1 megawatt. What is interesting about all this is that it is a blend of different technologies in which we see different various methods which interleave, such as software, hardware, mechanical design and firmware. In order to understand in a better way what power hardware in the loop is, there is a simple illustration here. In a classical development cycle, when a development team, an R&D team, wants to develop something like an inverter or any other device in power electronics, usually the classical flow is to start with an idea, go to a simulation model, simulate it and validate the model, then probably also speed up the simulation by means of using the real-time simulator. And this is usually where the development flow would stop, after which the product would be, the first prototype series would be produced and it would be tested in the laboratory. Power hardware in the loop extends this concept of simulation by means of bridging the gap and merging the simulation environment together with high bandwidth amplifiers, power amplifiers, which are actually something that is the core competence of EGSTON Power, in order to get a fully fledged and efficient framework for testing devices even before they are actually produced. The added value of this is that not only the concepts are evaluated at the simulation level, but the voltages and currents which would be generated in the model would be translated and transposed to the megawatt area, where EGSTON Power Amplifier would have the capability to produce these with high bandwidth. This essentially means that any device under test which would be connected to this would actually interact with the entire system and also with the simulation. This results in speeding up the entire development cycle, since we know that every prototype iteration that is usually done in power electronics at this power level is pretty tedious and time-consuming. One of the examples that we could present here in order to better understand the power hardware in the loop concept is a simple use case in which one of EGSTON amplifiers could simply play a role of a PV panel or a battery, or simply to be a grid. That is maybe one of the best cases to show that by means of emulation we can emulate both DC and AC use cases with the same amplifier, which is of course an added value to the system like that. Usually many systems which go in this direction support only DC or only AC, or they are limited to one single energy flow direction, meaning that they are not 4-quadrant, but rather they are 2-quadrant amplifiers. We can see also that EGSTON Power Amplifiers can be used in order to facilitate and to speed up the automated testing of devices under test, which can be pretty much anything when it comes to AC use cases. It could be inverters, it could be systems regarding wind turbines, it could be also DC related, something like a PV panel or a battery. So there are many use cases for an amplifier whose characteristic is actually to be highly versatile, programmable, and which can be used in many different scenarios simply by means of reprogramming it. One simple example of what the internal architecture of such a setup would look like is illustrated in the following figure, where we see practically the amplifier on the right side, the real-time processing engine in the middle, and the control PC on the left side, which is practically the setup needed for testing a device under test, which is connected to the outputs of the Compiso system unit, which is one of the name of one of the EGSTON amplifiers. One interesting thing about this entire setup is that the flexibility of the system allows easy reconfiguration, so that there is no need for massive recabling, massive firmware updates or software updates. The only thing that the user needs to do when he wants to test another device under test is to remove the current device under test, connect the next one, be it from a different family or not, and then simply start the system, configure it, and in a couple of minutes there is a completely different use case scenario which is going on. This is a very important aspect to emphasize, that in order to make this system running, Compiso system, several disciplines are actually needed to interleave at the same time in order to create an efficient design. Mechanical design in order to fit the energy density in the smallest package possible. Firmware design for controlling the power electronic elements which are in the system, and also the software design, which is on one side the control software interacting with this underlying hardware that is the amplifier itself. The better an engineer understands what the other element in the system is doing, the easier it is to develop the concepts for, be it software, firmware, or hardware. Therefore, we like to emphasize that the system that EGSTON Power provides should not be seen as an all software solution, because it is not. It should not be seen as an all hardware solution, because it is not. It is an interdisciplinary, heterogeneous solution that merges several disciplines in one single functional product. For every amplifier that EGSTON produces, there is the need to have a graphical user interface and reliable way for the user to control the system. There are several approaches to this. One of them is to develop a graphical user interface where the user interacts by simple keyboard and mouse interaction in a graphical oriented way. However, EGSTON also offers scripted way of controlling the system, where the user can automate certain procedures by means of using an API to the system without the need to open the graphical user interface and interact with it in the classical way. On top of that, there are functional layers that EGSTON implements which allow for the user to transform the amplifier into a fully fledged PV panel in terms of electric behavior. Therefore, the customer doesn't have the need to buy one PV panel with characteristics which cannot be changed. Rather, instead, he would buy an amplifier with a software layer on top of it, which transforms this amplifier into a configurable PV panel, or in other cases, it could be a battery emulator, it could be something else. The technologies that we use in software in order to meet all these requirements and make the system functional and running range from C++ and Qt Creator over remote procedure calls, gRPC, to databases, MySQL. But it is important to emphasize that the technology stack that we use in order to develop software also depends on the concrete product and the project. Therefore, we try to tailor the needs for such a complex heterogeneous development in a way that we do not make assumptions what would be the most optimal way, but rather we explore a little bit and then we settle for the solution that has the acceptance of the team, where the team is also most comfortable in understanding that that is the right way to proceed. There are also frameworks which we use, test frameworks for automated software tests based on Python and robot framework. There are other technologies that we use for continuous integration, continuous development. However, it is very important to understand that all these methods that we use are pretty flexible. We are trying to find the proper method and not the other way around. And it should be actually something seen as high degree of freedom in order to let's say, concept the way how the product is developed. Apart from the software, the similar paradigm applies to the firmware and the firmware technology and the challenges that we have. Unlike the classical software graphical user interfaces, which actually run on classical desktop PCs and essentially are non-real-time, we have the need for real-time firmware layers in the amplifier itself, because the amplifier has real-time deadlines. In order to produce voltages and currents at its output, it has to react quickly. The regulators have to do what they have to do, and for that real-time engines are actually needed in the amplifier, and for that we have also pretty interesting technology stack which we use inside, based on SoC, system on chip technology, FPGA, to microcontrollers. In terms of embedded programming, as we already know, on system on chips, there are embedded microcontrollers for which we can use either a bare metal approach or embedded Linux using C or C++ in order to optimize it with some real-time flavors to it, but also non-real-time flavors where we practically need to establish a TCP IP communication in order for the graphical user interface to interact with it properly, to communicate the status of the system back to the graphical user interface, and so on. The hard real-time features which the amplifier has to have with the highest degree of reliability are implemented in the core FPGA technology by means of using VHDL as hardware description language, along with some other methodologies which we use. And similarly to the development of the software, this is also, the firmware development needs to be seen as an interdisciplinary approach in terms of interaction with the hardware and software being maybe also some sort of a man in the middle or layer in the middle. in which, with respect to that, we can say that the technology stack that we use is also adaptable. This is something that we try to adjust every time when there is a product change or when we see that there is an interesting component on the market, when we learn also from previous lessons how to proceed further. And therefore we are always trying to continuously improve our approach to developing firmware in an optimal way as it belongs to a product such as EGSTON Power Amplifier Compiso. And if I could conclude, and the message that I would like to convey would be actually that EGSTON Power develops various technologies which cover high power power electronics test devices, automated solutions up to 1 megawatt, including signal generation in real time, but also signal acquisition in real time, meaning that the measured values can also be stored in real time. They can be stored for post-processing, for the evaluation of standardized tests, or simply for evaluation of any ad hoc test scenarios that we practically, that a user can have. The nice closure would be actually to say that in order to accomplish objectives which are quite challenging, we would like to, let's say, highly welcome anybody who is interested in the technology that is presented, be it from the software or firmware perspective, or maybe even some other perspective. There's always a way to find the right place in the company if there is enough interest for the technology stack that EGSTON develops. Me personally, I really like it because one thing is for sure, it is never boring, it is highly dynamic. There is a lot of potential to learn, many challenges to be confronted, but also in certain cases, depending on the need, there are also some routine work, things that need to be done if the developer wants to go that way. So regardless of your affinity, it would be good if you also, let's say, if you would also express interest in contacting EGSTON Power, as we would be really looking forward to it. So, thank you.